So we're going to begin our discussion of the measurement unit talking about units. Units not in terms of a group of concepts, but units in terms of how we measure different properties. So when we have a measurement, we will measure lots of things in this class or use measurements that other people have told us that they have measured. It's always going to have two parts, a number part and a unit part. So the number part is the digits that we're used to seeing in math, but the unit is now describing what property is this being measured, what unit of what property. We don't tend to see units as much in math class as we do in science class, and the units start to become very important. There's a few properties that are actually unitless, but for the most part, all the ones we're going to be dealing with are going to be have units. So some of the units can be a little bit funny. So for instance, when we talk about money, the dollar sign is a symbol unit that comes before the digits. So that's a little bit unusual, but they all are going to have some kind of unit. So grams, sometimes they're multiplied units, like joules second. We have an agreed upon system called the fundamental SI units. SI units are Système International, and it is a set of units that scientists have agreed on globally. There are 7 fundamental units because they can be measured by some fundamental phenomenon, like the charge of an electron. And so it's something that like everybody can measure and get exactly the same answer, and then we defined this unit based off of that. So we have mass, length, time, temperature, current, and amount of substance. And we have, for many times, they're the base unit in metric, but in sometimes, like for mass, it's kilogram. And then we have some ones that you're like, I don't know what current is. That's okay. So these are the 7 basic ones, and then all the other units can be derived from these. For instance, you don't see volume in here, and yet volume is something that we measure very frequently, but volume can be derived from this. So these are these derived units that NIST has said. So in others, I can see that a volume, it's meters cubed would be the SI unit, area would be meters squared, velocity is meters per second, acceleration is meters per second squared. So I'm using the meters and the seconds and deriving these units. And then these are some more units we'll be studying later on, a few of these later on in the semester. It is helpful to know the units of various properties. Now, not all of these are SI units, they're not the standard unit, but they're other units, but I can do conversions between the standard unit and other units. And if I understand a unit like pound and what it's associated with, that's a tricky one because technically pound is associated with force, but we tend to associate it with mass. Or joules is an energy unit. So when I see joules next to a measurement, whether or not it says it's energy, I know that it's energy. And that's a very handy skill to have when you're working in word problems. Sometimes it's not clear what your measurement is, what property it is, and the units can sort of identify that for me. So you should be familiar with some of these units so you kind of know which ones go with which properties. By the end of the course, they'll have a few others, specific heat, molar mass in particular, but we'll worry about those later on. We're also going to use prefixes for these SI and metric systems, and you're probably familiar with them. I'm sure you've seen them in grade school and in high school before, but it is important to know these prefixes because you'll have to be able to do conversions between the base unit and a prefix unit based off knowing these prefixes. So if I say, here's a certain number of grams, how many kilograms is it? You'll have to do that conversion, and that conversion will require that you know that kilo is 1,000. These blue ones are the sort of more frequently used ones, especially in chemistry, and we see that there's a variety of these. These are the exponential notation. The exponential notation is what it replaces. So for instance, when I refer to a gigameter, the giga part means it's 1 billion or 10 to the 9 meters. So 1 gigameter is 10 to the 9 meters. 1 millimeter is 0.001 meters or 10 to the negative 3 meters. So understand how to use this and how to make your equalities. That will become important shortly. Also, I want to talk about E-notation, scientific notation and E-notation. Again, hopefully you've at least seen this before in other classes. We will use this very frequently in chemistry because oftentimes we're dealing with measurements that are very, very huge or very, very small. And therefore it's easier to like not show all the placeholder zeros and just show the number with a exponent. The exponent is sort of indicating what place those digits go in. So we always have a number. The number begins with a non-zero number between 1 and 10. So it's a 1 digit, and then a decimal point, and then any others. And then I multiply it, have a multiplier of, well, what place value do these go into? So positive exponents are going to tell me that I'm going to multiply it by a large number because positive exponents indicate big numbers, and I'm going to end up with a large number. Negative exponents is going to tell me that it's a very small number. So I can, this is the standard notation, 6.13 times 10 to the 4. So I could figure out what 10 to the 4 is. That's going to be 10,000. So 6.13 times 10,000 is going to be 61,300. So I'm doing that in my head. You can do that with a calculator. So the other way I can do this is to just write the E, either small case or large case, to sort of indicate the times 10 part. So the 4 after the E is the exponent. This is far easier to type, right? This is hard to type, especially, the 4 should be superscripted, so that's harder to type. So calculators, sometimes different notation in different programs, different simulations, so sometimes entering things in. So these are considered equivalent. 6.13 times 10 to the superscripted 4 is the same thing as 6.13E4. And sometimes this is a little e, sometimes it's a big E. Sometimes on calculators it's 2 E's or EXP. So in that standard notation then, we don't have a multiplier. It's just a single number. And so with standard notation, and I can see that if I want to convert a number from scientific notation to standard notation, I see that 4 is a positive number. I'm going to be making a bigger number, so I'm going to move the decimal place to the right by 4. So 1, 2, 3, 4, I get 61,300.